Alright, welcome back to MME 436 one more time, and today we will start new topics: electromechanical system or modeling the mechatronic system. So on this part actually we'll cover mainly the uh, DC motor. Okay, we'll cover the DC motor. So before starting the DC motor, actually I want to show you one thing. So like, you know, if you have a coil like this, and if you apply voltage to this coil, then the current will start flowing through the coil. Okay, current will start flowing through the coil. So like here is the BS source voltage and the current I is flowing through the coil is nothing but the inductor, right? So it has inductance, and by any chance if you can place a iron rod through the coil, so can you guys tell me what will happen? So motor is basically based on this principle. This is called solenoid, right? Solenoid. So once the current will flow through the inductor, it will basically create a magnetic field. And actually there are north and south pole will generate. Okay, north and south pole will generate. Now if you change the direction of the current flow, then this north and south pole will flip instantly. Okay, will flip instantly. So this is the called solenoid. Motor is also basically based on the same principle. It's called the Faraday's law of uh, induction, right? Electromagnetic induction, I believe. So it's Faraday's law. Okay, so on a motor actually we have two magnetic field. So one is the rotor itself, like this is the rotor itself a magnetic field, and the the static field, this is also another magnetic field. And so we know that same type of magnetic field, they attract themselves. Like if you place north pole of a magnet and the south pole of a permanent magnet, they will attract themselves, right? They will try to attract and try to be one. But if we place the same pole, like north pole here, another north pole here, they basically repulse, right? So there is a repulsive force who acts between two magnets. Okay, the electric motor is based on this principle. So the when the actually we generate either electromagnet to the rotor, or we replace the electromagnet with permanent magnet, right? So like here is south, here is north, then here is south, here is north, and then here is also south, like this. So when the south pole align with this south, it basically apply repulsive force. When the north pole align with the south pole, it basically attract. So now if you can change the field continuously, like this is south pole, so it's like attracting north pole, and after that if you again change it to the north pole, so then it will repulse. So that basically if you change the magnetic field on these two, actually in real motor we have actually many magnetic poles, so then the motor will start rotating. So often we say that brush motor and brushless motor. So the thing I was talking about, the principle that we are continuously change alternate the alternate the field coil or field magnetic field. So as a result the motor rotate. So that's how the motor works. And now once there is a coil, actually this coil has some resistance and also this coil has some inductance. Okay, and one question, good question or good thing is, why why we place the core or iron rod or bar inside the solenoid. So we place it to make the magnetic field strong to produce strong magnetic field. Okay, because the produced magnetic field it also depends on the material inside the solenoid. Okay, that's why we place the iron rod or iron core, ferromagnetic core, right? So the thing I was talking, so once it's a coil, it has some resistance and also it has some inductance. So we have two coil, one for the armature magnetic field, another one is the stator magnetic field. Okay, so one for the, so like if you consider this one, so this one is this part, this one is related to the armature magnetic field, and this one is this resistance and inductor is related to the field, right? Magnetic stator magnetic field. And now, when the current flows through the solenoid, the magnetic field that developed, it depends on the amount of current that flows through the solenoid. The same principle is applicable for the motor. Okay, same principle is applicable for the motor. Like at any instant, the motor, the field, so motor field current, the motor magnetic field, uh, stator magnetic field, it depends on the field current. So stator magnetic field, if we say this is the stator magnetic field, and this is proportional to the field current. Okay, very similar to the solenoid, the amount of magnetic field produced, it's proportional to the current. If high current flows, then a strong magnetic field. If low current flows, weak magnetic field, right? It will produce weak magnetic field. And now the phi, the field magnetic field. So here let me write stator magnetic field. Stator magnetic field, it depends on the current through the field. It depends on the current through the field. And now the torque produced, the torque produced on the armature. So before that, actually we can talk about the like the torque produced on the motor is basically the torque produced on the armature is proportional to the stator magnetic field and also the current through the armature. Okay, also the current through the armature, so is proportional. So here we introduce the proportional constant. So at an instant the motor torque is proportional to the field stator magnetic field here is the armature current, and here is the proportional constant. So from this expression we can see that the motor torque tau Tm or tau m, whatever you say, is equal to K1, which is the armature magnetic field constant, Kf, which is the stator magnetic field constant, If, the current through the stator or the field, and Ia, the current through the armature. So look here, we have couple of proportional constant here. So this is proportional constant, this is proportional constant, and now we can establish the linear relationship between the motor torque and armature current or field current by keeping one constant. So like um, so if you keep the field current constant, then the motor torque will be proportional to the armature current, and if we keep the armature current constant, then motor torque will be proportional to the field current. So we'll analyze both, but first start with the field current. Okay, so here field current CURRENT current, or I would say stator current controlled motor. Stator current controlled motor. So in that case, what we get? So we get the motor torque tau m is equal K1 KF I A, this all are constant, then IF is equal Km IFS. So this is called the total motor constant, and the motor torque is proportional to the field current. Okay, motor torque is proportional to the field current. And now if we apply Vf, that is if we apply V volt to the field, so basically it will be equal to the Rf field resistance If is plus Lf is If is. So it will be equal to the resistance of the field plus the load, I mean due to the inductance of the field coil. Okay, inductance of the field coil. So let me show you the equivalent circuit. So like here is the resistance, and then here is the inductor, and we are applying the voltage here. So here is the field voltage, and R is the field resistance, L is the field inductance. So in that case, what we can write based on the KVL, Kirchhoff's voltage law. So Vf equal If is R plus L is If is, because actually it was I R plus L di over dt. So that's how after the Laplace transformation this expression comes. So from here we can write the expression for the field current IFS equal VFS over R plus LS. So this is, I mean, F because of the field inductor and field resistance. And now let's discuss about the mechanical side. Okay, so mechanical side, so at an instant motor torque tau m is equal load TLS plus TDS. So load plus the disturbance torque, the summation of this is load plus disturbance torque. If there is no disturbance, ideal case, this is equal TLS, only the load torque. Okay, and now so here is the thing. So like here is the motor bearing. So motor bearing is here, and here is the motor load. Okay, motor load considered, the inertia is J. So then if suppose if we apply the torque tau, or if the motor torque is tau, so basically tau equal J theta double dot plus the torque required to overcome the friction. So overcome the friction, basically b theta dot. Okay, b is the angular velocity and theta double dot is the angular acceleration. So we can write tau s equal j s square theta s plus b s theta s. Okay, and now if there is no motor disturbance torque, so basically tau m, that is motor torque, is equal, so tau m, I mean m, this is equal, is basically km I fs, right? So can you remember what was the km? So the km was the total motor constant. So here, look here, so total motor constant, which includes the proportional constant for the rotor, for the stator, and also we considered the armature magnetic field is constant and the corresponding current flow is IA. So we can write km IIF. So now basically IF is equal, I'm sorry, so now from here actually we can show the whole system in the form of a block diagram. So like VFS, we are applying the VFS, the field voltage to the field motor field. Okay, so we are applying this voltage to the motor field, and the motor field equation is 1 over RF plus LFS, right? And when we are applying the field voltage, basically the current is flowing through the field circuit or field coil, and as a result, like the current IF, this is the amount of current that is flowing through the field, and here is the proportional constant Km. So this proportional constant Km. So after that, what will come out from here? The torque, motor torque. Okay, the motor torque, and the motor torque, and if some disturbance will add at this point, if there are some disturbance. But if you do not have any disturbance, that will directly go to the load. Okay, that will directly go to the load. On the load, what we have the inertia and we have the friction. So basically, if we write the transfer function here, so theta s over tau m s equal 1 over j s square plus bs. So here, so input is tau m, output is theta. So 1 over j s square plus bs, input is the tau m, output is the theta. So output is the theta. But actually, what on the lecture note you will see, basically we use one more step. So 1 over s, so we bring it outside. So basically js plus b theta dot here and 1 over s here. So this is the position. So that's how the I mean the motor circuit. And now so now if I ask you to determine the transfer function between the motor voltage, okay, motor field voltage and the output angle, that is theta. So how you will calculate the theta transfer function with theta over Vf. So theta over Vf is, so I'm talking about this. So now we know the individual block, but how we will calculate the transfer function between the theta s, the angular position, over the Vf. So how you will do that? You will basically multiply all of them together. So from here to here, so from the beginning to end, you will multiply them together. So look here, if you multiply them, then you will get Km at the numerator, and the s we wrote there, then multiply by js plus b plus sorry, multiply by LF S plus RF. So which is basically the inductance of the field, resistance of the field. Here is the load inertia and bearing friction. Okay, here is the bearing friction. So we can rearrange and we can write this equation in the form of Km over J LF. So basically all are constant. So S multiply by S plus B over J, then multiply by S plus RF over LF. Okay. So later we will learn, the first order system and time constant. So I'm a little quick. These two are basically the first order system. The first order system response, I'm showing it very quickly, is something like this. Okay, and then the time required, 63.7% of the steady state. I mean this, the time required from 0 to 63.2%. This is called the time constant. Okay, tau, time constant. So here we can see that two first order system, and both has its time constant, and the time constant one is like this, another one is like this, and this is for the mechanical and this is for the electrical. So that means electrical will be, will reach to the steady state very quickly, whereas the mechanical will take more time. Okay, mechanical will take more time. So this is called the slowest mode. Okay, slowest mode, and this is called the fastest mode. So basically if we neglect the fastest mode, then it will not affect the system dynamics. So in that case, actually, if we write Km over J LF over S multiply by S plus B over J, so we can neglect the fastest mode, and we can only keep the slowest mode, and this is the transfer function, that is theta S over BFS equal Km over JLF over S multiply by S plus B over J. So we can see from this transfer function, for a system, actually, if we know only the inertia and the motor coil inductance and the friction, so basically we can develop the transfer function between the angle and the field voltage. Okay, so that's all for this session. So next session we will show you, I will show you how to develop the transfer function for armature controlled motor. Okay, armature current control motor. Thank you.